all of you turned in your magnetic field Earth's assignment. If I did not call your name, a couple things happened. Either your power and internet was out and you couldn't do it. I get it. How many of you all Thursday, Friday had no power and or internet? I got it. Okay. Or shocking, you did it and you forgot to click turn in. So if I did not call your name and you know you did it, you probably just didn't click turn in. So go ahead and click turn in and everything will be right with the world. If you couldn't do it because of beyond your control circumstances, get it done. Correct me if I'm wrong, those of you that did it, it's a quick assignment. Not super tough. How many of you all watched the video that I attached to the assignment? Awesome. So I braved the elements. I came in Wednesday night. I sat down and I read through the lesson and I made fun of them for getting things wrong and for like 2 people. Anyway, it's there. It's there. Kaya had trouble loading it, but nobody else did that today that actually looked at it. So I don't know. It might have been your internet. Our internet, our house, the reason I had to come in is we had internet, but I think maybe because the cell phone tower was like plastered with an inch of ice, maybe that's why it was slowed down. I don't know. We were able to get on YouTube barely. Like you ever go on YouTube and the video quality is really low? That's what it was. We couldn't get on most of our streaming services. I couldn't get on Infinite Campus. I could not get on CK12 to assign a lesson. I could get on Google Classroom, but I couldn't get on CK12, so I came in. Braving the bad roads, the main roads were already clear by Wednesday night, but the back roads that we live on, ooh, sketch. And I was in a 97 Neon. Right? Just ease on through. Easy. Okay. So there we go. Earth's rotations is what's up next. I have not assigned it to you. We are going to plow like a snowplow through this. We're doing 2 today. I know. It's a shortened class period. I don't care. They're easy, guys. Guys, listen. This is the Earth, right?
Yeah.
No, it's a model. Guys, it's just a model. This is not the actual Earth. This is the Earth. This is a model of the Earth. Don't get it twisted. Okay? It's the floor, but it's directly on the
Dirt? No.
Earth, right? Okay. And the Earth
Spins. Rotates.
spins. Okay, I'll take spins. I'll take it. It rotates or spins on its
Axis.
of rotation, which, if you can imagine a skewer right up through the butt and out the top of the Earth, right? Just why? Okay, so skewer. Talk about that, and then I'm going to say, has anybody ever had, has anybody ever not had shish kebabs?
Huh? What?
Take a skewer, and you take your little pieces of meat, and you push it onto the stick. And then you take a piece of a green pepper, and you push it on the stick, and then you take a piece of onion, and you push it on the stick, and a tomato, and you push it on the stick, and then you get another piece of meat. Maybe the same kind, maybe a different kind. Some people like to mix up their chicken and their beef and their pork or whatever, okay?
No.
No? You've never had that?
No.
I'm very disappointed in you. You need to ask whoever it is that does the cooking, or maybe you can volunteer. Yeah. Look up a video, how to make a shish kebab, okay, with different ingredients. A kebab, sure. You need to have one. Who's had one? Put your hand down if you never liked one of them that you had. Oh, you kind of liked it? Raise your hand high if you really like shish kebabs, whatever they call them. Yeah? Okay. All right. Anyway, the Earth rotates on its axis, which is an imaginary line that runs from the south to the north or the north to the south pole. Yes? Is this advanced stuff?
No. Nah.
Fantastic. And it rotates
diagonally
one time all the way around every
year.
365 days.
A month.
Month.
A day.
A day. 24 hours.
24 hours. Oh my gosh. 24 hours, guys. The day-night cycle on planet Earth lasts
A day.
24 hours.
a day or 24 hours. It's the same. Okay? All right, cool. Good. We are back up to third grade understanding. What?
If it spins, how come when you look up, you're seeing it spin?
Oh, but don't you? The question is, if the Earth is spinning, how come when you look up you don't see it spinning? Shame on you. Have you never gone outside at night on a clear night and looked up and realized that over the course of the night, the sky is rotating around you? So to a casual observer, guys,
I never looked at this guy.
I believe you. Never been outside at night. I believe you. Okay. To a casual observer, somebody that doesn't know any better, they just go outside and it's the morning and the sun's coming up over there in the east and it goes up and it goes down in the west and then 12 hours-ish later they see it come back up over there. Wouldn't you think it's going around us?
Now we're going around it.
Back in the day, there was this Earth-centric model where like everything rotates around, or revolves, not rotate, everything revolves around the Earth. Because if you go out at night, the whole night sky goes up in the east and down in the west. And in the daytime, the sun comes up in the east and goes down in the west. You'd think maybe. Now, once people started doing more detailed observations, you started to have folks like Copernicus, Galileo, that said, I'm looking at these other things, like retrograde motion with Mercury, like what's up with that, right? So they started putting 2 to 2 together and doing some calculus or whatever they did, and they said, maybe, we'll get to that. Okay, so we have established Earth rotates on its axis, which is an imaginary line from North and South Pole. Cool. There it is, guys. Look.
Whoa.
That's the picture of it. Axis, rotation. If you're looking above the North Pole, here's the North Pole on our model. If we're looking at it here, it would be spinning counterclockwise. Okay? That's the direction it spins. If you're over the North Pole looking down, the Earth is rotating in which direction? Counterclockwise. Okay, cool. Also, if you're over the whole solar system, let's say you're over the sun, north of the sun, looking down at the North Pole of the sun. Yes, the sun has a North Pole. Yes, the sun rotates on its own axis. The whole solar system, except for a couple of objects, rotate or revolve around the sun also in a counterclockwise direction. Okay? Couple of exceptions. The exceptions are called retrograde. Anyway. Day-night cycle. Guys. Day-night cycle. Earth spins. The sun stays in the same spot relative to the Earth. Yes?
I thought it went over.
Relative to the Earth, the sun stays in the same spot.
And how is it?
Wow. Okay, we'll watch a video. It might help you. Okay, so we're gonna pretend. Let's pretend we got some third grade work to do over here. That's okay. It's okay. Let's say this hat is the sun. Is everybody paying attention?
Yep.
Okay, this is the sun. This is the Earth. Northern hemisphere on, as we're looking at it, the top. There's no up and down space, by the way. Okay, so if the Earth were tilted like this toward the sun, the northern hemisphere toward the sun, what season would it be?
Fall.
For us?
Summer.
All right.
Winter. It would be
In the northern hemisphere, we're rotating on our axis, and we're going around the sun. But at one point, just pick a day, if that northern hemisphere is tilted toward the sun, what season would it be in the
Summer.
northern hemisphere?
Summer.
Summer.
What
Okay?
about the side?
Now, as it's still spinning, just pretend this is still spinning in my hand. Okay, can you do that?
Yeah.
All right. As it rotates, a few months later, it would be over here. Okay? Now the axis isn't pointed toward or away from the sun. It's like perpendicular to, I guess, 90-degree angle to. Does that make sense? You would be at what comes after summer. Fall. No. One season next, you've gone 90 degrees through the rotation. You were in summer in the northern hemisphere. Now you're in fall. Okay, in that middle part of fall, you're going to be at the
Equator.
equinox. The fall equinox. Which means the way you're oriented, whether you're in the northern hemisphere or the southern hemisphere, you're going to have equal length day and night. Okay? The 24-hour period at the equinoxes, I don't know, we'll have 12 hours of sun, 12 hours of night. Okay? Now, 3 months later, now how is the northern hemisphere oriented to the sun?
Winter.
It's pointed away, so it's winter. Okay? 3 months later, it's over here, still oriented the same way. Whoops.
Spring.
How did I start? It would have been like this,
Spring.
right? So now it's pointed away. Where did I start? I'm confused. Did we just do winter?
You started over
Did we do winter?
You started summer.
Started on
Okay.
the side.
You get it though, right? As it goes around, it shifts. If the axis is pointed toward the sun, that hemisphere is going to experience summer. If that hemisphere is pointed away, it's going to be winter. If it's halfway in between, you'll have equal length day and night. The day-night cycle on Earth is 24 hours, yes? If it's winter, will you have more day or more night?
More night.
More night in the winter. But the total will add up to 24. Okay? Moving on. Yes, yes, yes. Next lesson. All right. We were starting to talk about Earth going around the sun. And we talked about the Earth-centric model, where everything went, no, we said, no, it's the Earth's probably not at the center. The sun's probably at the center. Well, how did we get to the heliocentric model, sun at the center? How did we get there? Well, observations like this one. Galileo was looking at Jupiter through a telescope, and he noticed some moons, some objects, some satellites going around Jupiter. From night to night, you could see they were moving around Jupiter, orbiting around Jupiter. Smaller objects orbiting around a bigger object. And he put it together in his head with other observations that he and other scientists like Copernicus were making. And he said, well, if smaller objects, I can see, easily see, smaller objects going around bigger ones. So we have planets with moons going around them. If moons go around planets, what's the biggest thing in our solar system?
The
The sun.
The sun. So if moons are smaller than planets and they go around planets, planets are smaller than the sun, so shouldn't they go around the sun? And with the other observations they made, they came to the conclusion, yeah, the sun is in the middle, and all the planets go around the sun, and then the moons go around the planets. Yes? Okay. What is right, or you can tell me what's wrong, I don't care, with that image? So we've got a picture of the solar system, a model / picture of the solar system. It's not a picture.
It's not.
That's not like a What's not accurate about it?
The distance.
The distances. The scale.
There's no, yeah.
Right? The distances of the planets from each other and from the sun, and
Size.
the sizes. So both the distances of the planets from each other and the sizes of them in relation. Now, do they kind of, sort of, vaguely get it right? Sure. You can see the inner planets are closer together than the outer planets are. That's true. Is it to scale? No. The planets, okay, you got Jupiter's the biggest. Mercury is the smallest. Is that true? Is the scale off? Yeah. Okay. So why do we draw things like this if they're not accurate? To put it in perspective, because if we did it to scale, on this size order, you wouldn't be able to see the smallest objects. Okay? So later this week, next day or two, depending on weather and icy conditions, whatever, I want to go outside. So you might need to bundle up if we're still cold. Of course, this part of the day, I think, we'll look at the forecast. We're going to do a scale model of the solar system. Okay? Yeah. All right. In your notes, because everybody's got their paper notes out, right? I got 1, 2. Awesome. 3. 3 people with paper notes out.
4.
4 now? Can I erase this stuff from last semester? Yes, I can.
Have you been ready?
Cooper, some more pencil.
What? Oh, nice. Oh, it's,
Mr. Ready? Can I go to the bathroom?
yeah, hurry up. You're not back yet? All right. So let's say that that's the sun. Can I make it smaller, please? By the way, my drawing is not going to be to scale either. So I'm going to make it like that big because it's like as small as I can make it and you still see it. Does everybody see that?
Yeah.
So that's the sun.
Wait, why is that?
Okay. We have, the order is good. I like this diagram, guys. I can't do it to scale either, so why am I going to knock it too much, all right? But note, what is right here in between the orbits of Mars and Jupiter?
Nothing. Milky Way.
The what?
Milky Way.
The asteroid belt. Guys,
What's
the
that?
Milky Way is the whole galaxy, guy. Come on now. So
What's
in
the
between, we got Mercury, Venus,
Earth. Mars. Jupiter.
Saturn.
Uranus.
Pluto.
But it's
Venus.
not a planet. Venus.
Venus is right here,
Oh,
dude.
Neptune.
Uranus and Neptune. Thank you. Okay. But what lies in the space between Mars and Jupiter? The asteroid belt. You can see it very faintly. And by the way, you can see this little dot of light there too. So there's asteroids right here. And then what's that? Does anybody know?
Milky Way.
You're being silly.
That wasn't me.
The Milky Way is the whole galaxy. Good grief. And then there's this thing out past Neptune. What's that? It's another asteroid belt. Did everybody know there's 2?
No, I didn't.
Okay, so we know for a fact, as of the 1950s, we know for a fact that there's not 1, but 2 asteroid belts in our solar system. This one is called the Keiper belt. Keiper. Okay? Yes.
What's that little dot below the...
Hold on, I'll get to it. Good question. Good question. Shh. Shh. If you don't know, don't say. All right, so we've got Mercury, Venus, Earth, Mars, asteroid belt. AB for asteroid belt. Got it? Okay. And then we have Jupiter.
Saturn.
Then we have Saturn,
Then Uranus.
Uranus,
And Neptune.
and Neptune. And then we have the Keiper belt. In the Keiper belt, we have what are called trans-Neptunian. I'm spelling that wrong. Neptunian. Help me out. IAN. Trans-Neptunian objects. All right. Hold on to your hats, folks. Trans-Neptunian objects are found in the Keiper belt, and they include things like Pluto.
Told you.
Pluto, as we understand it today, is the first trans-Neptunian object that we discovered. It was in the early 1930s. Don't ask me what exact day. Clyde Tombaugh, something like that. Was it? Did you know? Oh, somebody said the date. So Pluto. Now, guys, here's the problem. So we found our first trans-Neptunian object in 1930 whatever. We named it Pluto. We thought it was the 9th planet. All the way up through the early 2000s, it was known as the 9th planet. Yes?
Yeah.
Your entire lifetime, it has been known not as a planet, but as a dwarf planet, a completely different category. Okay? The International Astronomic something or other voted on it because what was happening is we were finding more trans-Neptunian objects. We found a couple that were about the same size as Pluto, and one or two that are actually probably bigger than Pluto. Eris, I believe, is one that they think is bigger than. There are others, though. There's Sedna, there's Makemake, there's... help me out. I can't remember them all. So they kept finding these other objects out there in the same neighborhood as Pluto. So they said, well, are we going to call all of these planets? Or do we need to do something? So what they did is they decided to create a new category, dwarf planet. Okay? So these trans-Neptunian objects, all of them that are about the size of Pluto, were reclassified as dwarf planets. Okay? So Pluto was demoted. Okay. A lot of people got upset about it. This little guy right here that you guys were talking about, that is Ceres. Ceres was first discovered in the 1880s, I believe, and was thought to be a planet too. And later on, they demoted it and said, no, it's just an asteroid. Well, because of the reclassification and this new category of dwarf planet, Ceres was upgraded to dwarf planet. It's not just an asteroid anymore. It's a dwarf planet. So we have dwarf planets in both of our asteroid belts. The outer one has a specific name, Keiper belt, named for the scientist, last name Keiper, 1950 something or other. He was like, I think there's like a lot of stuff out here. Okay. Now, this next one is not in the diagram, and I'm glad it's not, because to this point we still have not directly observed anything in it. But the data suggests that there's something way out further called, we've named it, even though we haven't directly observed anything in it, we call it the Oort cloud, O-O-R-T, the Oort cloud. And this is where we think most of our comets hang out. Okay? When I say hang out, I mean that's where they spend most of their time. Do you remember when we were talking about Kepler's, what was it, the third law, second, third law? I don't know, second. Objects in an elliptical orbit around the sun are going to be traveling the fastest when they are nearest to the sun. And they'll be traveling the slowest when they're the furthest away. So it stands to reason that if their orbit is like crazy elliptical like this, off in every direction, right? They'll be spending the most of their time out here because they'll be going the slowest. Does that make sense? So when I say that comets hang out there, I don't mean they're not moving back in. It just means they spend most of their time further out. Okay? So you got your planets, you got your inside asteroid belt, you got your outside asteroid belt, and you have the Oort cloud way the heck out there, we think. Now, all of these objects revolve around the sun. The sun has something like 99% of the mass in the solar system. It's nuts. Okay. Questions on that? Cool. The Earth, we already said, is about 93 million miles away from the sun. That's 150 kilometers. They also mention Mercury and Venus and all these. They talk about things and stuff. There's a video. Summary Earth's orbit. around the sun is somewhat elliptical. Earth's seasons are not caused by the shape of the orbit. Guys, we demonstrated, yes, that the way the axis is tilted and its position in the orbit around the sun determines Earth's seasons, not its distance from the sun. We will, later this semester, talk about some cycles in its orbit because the Earth's orbit isn't static. It doesn't stay the same every time it goes around. There's a wobble in the tilt, and there's irregularities and cycles in the revolution around the sun, okay? But I will say this. Pluto, out here in the Keiper belt, has a much more elliptical orbit. In fact, it's so elliptical that sometimes, about every 70 years or so, it spends a few years closer to the sun than Neptune. So back in the day when it was still considered planet 9, sometimes it was planet 8. Make sense? That's cool, because its orbit dipped inside of Neptune's orbit every 70 years or so for like 10 years, which means it probably only happened, what, once or twice, because it was only considered a planet for 80 years or whatever it was. Okay? But because Pluto's orbit is so elliptical, pretend this isn't the Earth anymore, pretend this is Pluto. When Pluto is in the closest to the sun, it is warmer than when it's furthest from the sun because of its proximity to the sun. Does that make sense? Pluto's seasons, it has seasons, are caused by its distance from the sun. Earth's seasons are not. Pluto's are. Does that make sense? When Pluto dips in closer to the sun in its orbit, its atmosphere, which is frozen in the wintertime on the surface, it evaporates and becomes gas again. Pretty cool. Look into it if you're interested. Mentioning comets. Last thing I'll give you before I turn you loose on the assignment. Okay? This is the sun. Okay? I'm going to redraw it. I'm going to redo this. If this is the sun, and there is a comet going around the sun, it's going to come in and go out. I'm going to draw the comet. And comets have tails when they're close enough to the sun, right? Because as they get closer to the sun, they start to heat up, yes? Because the sun's warm. And comets are made largely of ice, yes? Yeah, you do now. Okay, so let's say the comet is right here. If it's traveling in this direction, where should the tail be pointed? This way? Yeah. So if the comet's traveling this way, you think the tail would be like that? No. Yeah. If it's going in this direction, the tail should be trailing behind, right?
You're going to be like, wrong.
It's wrong.
Yeah.
Check it out. We think that because in Earth's atmosphere, if you're moving along really fast, the debris off the object is going to be behind it. There's no atmosphere in space. The source of the melting is the sun. The sun puts off charged particles. It's called the solar wind. So the tail is going to be blown away from the sun. So it's going to look like this. Look, check this out. If the comet's right here, it's traveling this way as it's swinging around. The tail is going to be that way. Still coming around. Let's say the comet's right here. It's on its way out. The tail is that way. This one freaks you out the most. If it's coming in way out here, the tail is like this. It kind of looks like it's behind it. If the comet is right here, moving away, the tail is like that. So it's actually moving into its tail. If it's going away from the sun, the comet's tail will be in front of it. Did you know that? Now you do. And I still don't have anybody with paper notes out. Okay, that's fine. Okay. All right, guys. Distance, some of the details you need for the questions are in the article or in the reading. Okay, 93 million miles from the Earth to the Sun. That's 1 AU. We talked about that last semester, yes? An astronomical unit. Mentioned some stuff about Saturn and its orbital period, right? Cool. We talked about that when we discussed Kepler's laws of motion, yes? Okay. So some of this should be, most of this should be reviewed. I'm going to go ahead and assign both right now. You guys have time, probably, honest to goodness. You're probably going to take less than a minute per question. There's only 20 questions. You're probably going to finish. Okay? So go ahead and do it. Don't think you won't finish. I'll do it later. Do it now.